Hello. So this video is to help you out with CKY, or with basically constructing a parse forest for a sentence, provided you have access to a context-free grammar. So here on the left, top left, I have my context-free grammar for this example. And I have a sentence: I eat pizza with anchovies. And I would like to try and find out what are all parse trees according to this grammar for this sentence. Well, if we have any, of course. You can see here on the left that I organized this carefully. So I have all the symbols, all the rules for rewriting S, all the rules for rewriting NP, all the rules for rewriting PP, all the rules for rewriting VP, and all the rules that introduce words. You see that this grammar is not actually in Chomsky normal form, because we have unary rules that are not terminal rules. Right? So the algorithm that I'm going to show you works for this. The only constraint is that the grammar is binary. Typically, you would see CKY be presented specifically for CNF grammars in Chomsky normal form, where these types of rules have been somewhat removed from, not removed, but you adjust the grammar such that rules of this kind are not there. There will be rules of other kinds instead. But it's very simple to actually include them, so I'll keep them around. Okay, the algorithm goes about as follows. We are going to go bottom up, trying to figure out larger and larger phrase categories that are nested, that are on top of other existing phrase categories. In each one of these boxes, I will have a phrase category that spans a piece of the original text of a given size. So for example, a phrase category in the blue box has size 1, so it might be a phrase category sitting on top of I, or sitting on top of eat, or sitting on top of pizza, and so on. A phrase category in the second box has size 2, so it might be a phrase category sitting on top of I eat, or eat pizza, or pizza with, or with anchovies, and so on and so forth. So when we get to this level, we have phrase categories that span 4 words. So we might have I eat pizza with, or eat pizza with anchovies. And of course, up here, we're going to have the sentence symbol. If we can derive this string, at the very top, we're going to have a sentence symbol that spans the entire sentence. So 1, 2, 3, 4, 5 words. I'm going to work with what are called fence post positions. So 0, 1, 2, 3, 4, 5. So if at one point I say I have a phrase category that spans from 0 to 1, it covers I. If I have a phrase category somewhere here that goes from 1 to 4, it covers I eat pizza with. So it belongs to this level. Okay. I'm going to present you CKY already with the so-called back pointer. So you will see that for any phrase category that we introduce in one of these levels, we'll have a mechanism to backtrack to the level below, understanding what phrase categories have been merged. And remember that because we're constructing trees, phrase categories are things like this. They span over an amount of text, a portion of text, and you can create a new category by, merging the two below, like in a little tree. Right, and then you can, merge the category A and the category D and the category E, and do something like this. Right, and then you have text down below. So phrase categories can only be merged into a more general phrase category here on top if they are adjacent, right? I can merge a B and a C under a D with a rule of this kind, but I cannot, merge the A and the C because there is a B in the middle. So you will see this as we work through the algorithm. Okay. All right, so let's start. The way we go about this thing is we have to go bottom up, trying to generalize our words into word categories, our word categories into phrase categories, and merging phrase categories that are adjacent as we go up. So we do that by finding in the grammar rules that support one parse action. Okay, so for example, here I have I, and here on the right hand side of my rules, I'm going to look for instances of the terminal I, and I found one here. Maybe I'll just show you here. Yeah, so I can map this to a pronoun, which would therefore, go from 0 to 1. I'm going to mark the symbol with the span that it covers, just to remember later on. Now, sometimes if your grammar has unary rules of this kind where this thing is also a non-terminal, when this is the case, you may be able to immediately rewrite the pronoun as something else, or to immediately derive a higher phrase category, another phrase category. So we would look for instances of the pronoun on the right hand side of a unary rule. So let's see, these are unaries, but these are terminals, right? So these are rules that introduce terminal symbols. Let's put a symbol, let's draw a line here. And let's highlight the unary rules so later we can find them more quickly. So these are unary rules, right? So they are unary rules with non-terminals on the right-hand side. So yes, we do have a pronoun on the right-hand side of a unary rule. So this means that we can immediately rewrite a pronoun into a noun phrase. I'm going to draw this as an alternative thing to do. You can have the pronoun and immediately, maybe I need more space. I can have a pronoun and immediately rewrite it as a noun phrase, also from 0 to 1. So these are two options for how to parse I into a phrase category, one or the other, that spans over exactly one word. All right? There are no, well, in principle we should continue, right? There can be a noun phrase on the right hand side of a unary rule, and we should check. There isn't. If there was, then we would have yet a third option. Let's pretend there was, okay? If there was, let's say there was a sentence rewrites into NP. Suppose this rule is part of the grammar. Then you would have a third option where from 0 to 1 with a pronoun, from 0 to 1 with an NP, you can eventually reach 0 to 1 with an S. And then you would have 1, 2, 3 possible alternative ways to parse I from 0 to 1 with a span, a phrase category that spans over exactly one word. So this last one was hypothetical, so I'm going to remove it. There we go. And now we continue parsing the next word. The next word is eat. So let's look for occurrences of eat on the right-hand side of a rule. Well, the terminal rules are here, and I find eat there. So we can generate eat from a verb or parse eat with a verb. So that will give me a verb from 1 to 2. And we should immediately check whether verbs appear on the right-hand side of a unary rule. And it does here. Hence, we have an alternative way to derive the same word, which is through a VP. From a VP, we generate a verb. From a verb, we generate eat. And see that these are two alternative ways to generate the same span of text. Are there VPs that appear on the right-hand side of a unary rule? No. VPs appear on the right-hand side of binary rules, but we are not there yet, and we are not at the point where we are merging spans. We are still basically covering spans of size 1. So let's move on to the next word being pizza. Pizza appears here. So pizza can be parsed into a noun from 2 to 3. And we should check whether nouns appear on the right-hand side of unary rules, and they do here. So we can also derive an NP. NPs themselves don't appear on the right-hand side of unary rules, so we move on to the next item, with. And with appears here and only here. So we know we can parse it with a preposition. And we should check if P's appear on the right-hand side of a unary rule, and it doesn't, so we are done. And we move on to anchovies, which is here in this rule. So anchovies can be parsed as a noun from 4 to 5. Of course, we know that nouns do appear on the right-hand side of a unary rule, so anchovies can also be used to justify an NP. And we should check, we already checked for N, let's check whether NP appears on the right-hand side of a unary rule. It doesn't, so we are done. And at this point, we are done with all spans of size 1. Now, when we move on to spans of size 2, we're looking for combinations of adjacent words or phrase categories that we can merge into a single phrase category. So we'll be merging two non-terminal symbols. Hence, the only relevant rules at this point, from this point onwards, are the binary rules. Right, we already dealt with the unary rules down here. We will be checking whether, once we do merge two categories under one, we will check whether that resulting category appears on the right-hand side of a unary rule. That we will do. But the very first thing we need to do in order to move from the blue box to the green box is to merge spans, because we need the spans to grow in size. Now, recall that these two are alternative ways to generate this one span here. So we will not be trying to merge these two things. They are actually competing for how to explain, for how to parse first position. What we can merge is pro with one of the alternative ways to continue from 1 to 2. So pro V or pro VP. So these are possible things to be merged, or NPV and NPVV. These are possible things to be merged, and so on and so forth. So these or these, this or that, this or that, and that's it. So let's get started. I'm going to switch to green. We're looking for rules that can be used to merge a pronoun followed by a verb. So we're looking for the purple rules. Pronouns are just not there at all. So there is no pronoun with verb, and there is no pronoun with VP. So this seems to be for now a dead end. Let's see if we can find ways to merge an NP that sits next to a V, or an NP that sits next to a VP. NPs do sit next to VPs. NPs do not sit next to Vs. So the first rule Okay, the first combination is not going to lead anywhere, but the second combination will help us. So we can merge an NP with a VP, right? And this gives us an S. This is the rule. And we have an S that goes from 0, from where the left, so there are two symbols, the left, the first symbol and the second symbol on the right hand side of the rule. Where the first symbol begins, that's where the S will begin. Where the second symbol ends, 2, that's where the S will end. We're literally concatenating those things. And see that clearly, the first symbol must end where the second symbol begins. So they both, they are adjacent in fact. Okay, so this is what we can do here. We should immediately check whether S appears on the right hand side of a unary rule. It doesn't. So we are good. There's nothing else we can do where we begin merging from 0, 1. Let's try to begin merging from 1, 2. That is, concatenate 1, 2 with something like that covers 2, 3, 2, 3. So we can try V with N's on the right hand side of a binary rule. I never find V and N, so this is a dead end. V and P. Nope, another dead end. VPN. Nope, there are VPs here, but not N. VPNP. Well, VP on the right hand side, VPNP on the right hand side. So VPNP makes a VP. And we can derive this. So we can concatenate the VP that begins, that covers from 1 to 2, with the NP that covers from 2 to 3. And what we obtain is the VP from 1 to 3. We should immediately check whether a VP appears on the right-hand side of a unary rule. It's not the case. One little trick. See that the unary rules, they only have word categories on the right. So we are basically never going to use them again. Because we know that from span 2 onwards, we won't find word categories, right? The word categories, they are all phrases with span of, with exactly one word beneath. Let's go on and now begin concatenating from position 2. So now we have NP or NPP. So right hand side N followed by P, and there isn't any. So this is a dead end. Right hand side NP followed by P, NPPP, P and P, the opposite. So that's also a dead end. Let's begin concatenating from the third position. So we can have PN or PNP. So PN, we have PNP, but not PN. But okay, we have P and P. So P for adjacent to an NP makes a prepositional phrase. So P adjacent to an NP makes for a prepositional phrase from 3 to 5. Okay, so we are done with level 2, spans of size 2. And we move on to spans of size 3. So let me change the color again. Now, how do we make a span of size 3? Well, we can merge a span of size 1 with a span of size 2, or a span of size 2 with a span of size 1. All right, so we are going to have a blue span being merged with a green span, or we are going to have a green span being merged with a blue span in this order. Right, this helps you because that's basically what we're going to have to, is the combinations we need to attempt. So let's try. Let's try blue followed by green. So a span of size 1 followed by a span of size 2. So what are our options for spans of size 1? We have pronouns or NPs. And we can merge this with an adjacent span of size 2. So a green span that starts from 1, which we know 1, we know at least 1. So we can try pronoun with VPs or NPs with VPs. Let's go have a look if we have rules for that. Pronoun followed by a VP on the right hand side. There isn't. NP combined with a VP on the right hand side, we have S. So we can derive an S symbol from 0 to 3 by merging the NP from 0 to 1, that is by concatenating the NP from 0 to 1, that sits right next to the VP from 1 to 3. And that's it. That's all we can do for this bit. Let's keep on trying to merge a blue with a green. And we move on the blue box. So now we're talking about 1 to 2. And we want to merge a span from 1 to 2 with a span that begins at 2, but extends over 2 words. So a span from the green box. So from 2 to 4. There is no span from 2 to 4. Therefore, there is no way we could obtain a 3-word long span by merging eat with something that we have already derived. So we move on to pizza. Now, pizza is covered by N or NP. And we want to find a green span that starts from 3. And we have one. We have a prepositional phrase. So we can attempt to merge N with PP. If we have a rule for it, we do not. And P with PP, if we have a rule for it, and we do. It's right here. So NP followed by a prepositional phrase will give you a noun phrase. So the NP, maybe I'll just push it a little bit like this. The NP and the PP, they will make another NP, this time from 2 all the way to 5. And we go on. So we just did pizza, now we're going to try with. We would have to merge a span of size 1 that starts at 3 and therefore ends at 4 with a green span of size 2, but, well, there's not enough space for that, right? We don't have enough tokens for that. So we're actually done with combinations of blue and green in this order. Now let's try to combine green and blue in this order. So what green spans we have, we're going to try to merge them with something that contains one word and sits to the right of that span. So for example, here we have a 0S2. We would want to merge it with something that covers from 2 to 3. So S followed by N or S followed by NP. S never appears on the right hand side of a rule, so this is a dead end. Let's try with the VP. VP 1 to 3, we want to find a phrase that starts from 3, so 3 to 4 has size 1. So VP followed by P. VP followed by P, we never have. We have VP followed by PP. So we cannot really merge these two spans over here. The next available green span is already at the end, so there is no way we can merge it with anything. So we are actually done with the spans of size 3. Now I'm gonna erase here my where I was bookkeeping what I have to do. Okay, now we want to derive spans of size 4. How do we obtain spans of size 4? So by merging, how can we obtain a span of size 4 if all we can do is merge spans from adjacent spans from below? So let's see. We can obtain a span of size 4 by merging two spans of size 2. Right, so spans of size 2 are green, so we would merge, sorry, I wanted to color code this for you. We want to merge a green with another, provided they are adjacent, right, into a span of size 4. The other way we can do is to get a span of size 3 and merge with a span of size 1. on one way, or the other way, of course. So we can also start with span of size 1 and merge with the span of size 3. And this is it, right? We can only obtain 4 words by merging 2 consecutive spans of size 2, or consecutive spans where one is size 3, the other is size 1, or one is size 1 and the other is size 3. Okay, so these are the 3 things we are looking for. Let's begin. Let's begin with 2 greens. So do I even have adjacent greens? Well, this is not adjacent, right? So it ends at 2, this starts at 1, so these are overlapping. They cannot be ever merged, combined via concatenation. These 2 are adjacent, ends at 3, starts at 3. So I can potentially concatenate a VP and a PP if I have a rule with that sequence on the right hand side. So VP and PP actually is supported by this rule over here. So a VP merges with an adjacent PP, forming a verb phrase that spans from 1 to 5, from where this VP begins to where this PP ends. Excellent. So we can derive a verb phrase of size 4 by merging 2 greens. And now we're out of greens, so there is nothing we can do anymore on this side. So this part is done. Let's try to work with 3 followed by 1. So let's get a span of size 3 and look for an adjacent span of size 1. I have a span here, so an adjacent span would be down here below in the blue box beginning at 3, so this is the only one. And I would have to be able to concatenate S and P. I know that there are no rules with S on the right hand side, so this is a dead end. My next attempt is this one. This one has size 3. It's at the end of the string, so there is no way I can merge it with anything. So we are done with this possibility. And now we're going to look into this possibility, the possibility of merging a blue with a reddish, pinkish span. So size 1 followed by size 3. Well, this is on the leftmost span, so there's nothing we can do with that one. It's a dead end, we already know, because it's an S. It's an S that doesn't span the entire string, and we do not have S on the right hand side of any rule, so it's literal dead end. But we have this noun phrase, and it begins from 2. So if I can find a blue span that ends in 2, so these are the options, then I could entertain a merge. It's going to be a V with an NP or a VP with an NP. Now V's followed by NPs we do not find. So our only option is VP NP, for which we do find a verb phrase. Now this is an interesting case, and I'm going to code it with a color that is related but not identical. I can use this VP and this NP to justify a verb phrase from 1 all the way to 5. Now, this symbol VP 1 to 5 has already been derived, but from a different path. So I do not duplicate the symbol. The symbol, I only need to derive it once. But I bookkeep that I can derive it one way or the other. And these are the famous back pointers. This is interesting. This shows me that there will be alternative ways to derive the same span. So there is a structural ambiguity here from this point onwards. We're actually done at this level because there is no other way to reuse this span. And there are no spans left at this level. So we are now done with spans of size 3. Now, the most rewarding. Let's make a box for it. The whole sentence. We are looking for ways to obtain a span of size 5, and we can obtain such spans by merging a span of size 5 with a span of size 1 on one way or the other. We can also merge two spans of size 3. We can also merge a span of size, oh, sorry, I made a mistake, right? We're looking for the whole sentence is a size 5. So this is all wrong. Let's start over. We can get 4 words, a 4-word long span, and concatenate it with a 1-word long span. We could concatenate a 3-word long span with a 2-word long span. Oh, either way, right? There's no other way, right? 5 can be 4 and 1, 1 and 4, 3 and 2, 2 and 3. Yeah, there's no other way to decompose this. So let's try. Let's begin here. An orange followed by a blue. So VP15, it's at the end of the string. There's nothing covering 5 to 6, so this is a dead end. Let's try blue followed by orange. So orange begins at 1, so the only blues available are these ones. Pro and VP. There is no pronoun followed by VP. NP followed by VP. There is a sentence symbol. So we can combine this NP with this VP and form a sentence from 0 to 5. And we're done with this path. There is no other way to derive a 5-word long span. Let's try pink with green. So this is a dead end. Let's try this one. This means, wait, if this is a dead end and this is at the end of the string, there is no way to do pink with green, but maybe there is green with pink. So we have pink from 2 to 5, so we're looking for a green from that ends in 2. And the only one we have is this one here, which is an S. So I already know this is going to be a dead end, and I know that because there is no way to combine S with NP, because S never appears on the right hand side of one of our rules. Therefore, this is also a dead end, this is also a dead end, and we're done with investigating these options. And we're done. We're in fact done. That's the only way to derive a phrase category with it spans the entire sentence. Okay, so what did we learn? We learned a few things. There is a way to generate the entire sentence from 0 to 5. So, I eat pizza with anchovies is grammatical under this grammar. It belongs to the language. That's the first thing we learned. We can also use this representation of the parsed forest to do a few things. We can obtain all parses. 2, we can obtain marginal probabilities. And we can 3, obtain the best parse. And I'm going to continue with the things. I'll take a short break and continue with the things in a moment. Hello. Let's start by talking about the inside algorithm. The inside algorithm is related to the forward algorithm, is the algorithm that will give you marginal probabilities. So what is the marginal probability we're looking for? Well, we're looking to sum every rule sequence such that the yield of the rule sequence is the sentence we want. So I eat pizza with anchovies. Meaning we are looking for all trees in this forest that will give us the right sentence. So all complete trees. And we're going to look to sum their joint probabilities. This is the marginal probability we're looking for. This is the probability of a sentence. Well, the sentence that we're given, this one here. Let's begin by doing it by hand. So to do it by hand, we need to be able to figure out what are all trees that are good parse trees for this sentence. We can do that recursively from S. So I'm going to do it here. So we start with 0S5, and then we generate an NP and a VP. So now we're going top down. We generate an NP from 0 to 1, and adjacent VP from 1 to 5. Great. So I'm going to draw here also on the side what this looks like. This looks like something like this. Actually going to space this out a bit more, because as we see, the VP is very long, right, from 1 to 5, and the NP not so much, from 0 to 1. Then we get to the VP, and at this point there are two things we can do. We can derive it one way or another. So we can derive it by concatenating a VP from 1 to 3 to a PP from 3 to 5. That's this option here. Or we can derive it by concatenating a VP from 1 to 2 with an NP from 2 to 5. And then you see that now we actually have two trees going forward. We can have a VP from 1 to 3, or it splits to that is next to a PP from 3 to 5, or we have another tree where the VP is made of a VP from 1 to 2 and an NP from 2 to 5. See? So far we have two options. So let's recursively continue from the first option. So we need to expand VP13, right? We always expand the... oh, my bad. Let's do this more systematically. For a moment I didn't do it very systematically. We started here, SP and PVP. We always expand, in generation, we expand the leftmost non-terminal symbol. So we are actually preoccupied with NP1. Forget VP for now. I'll leave it here. For now, just forget it. We should actually be generating NP from 0 to 1. NP from 0 to 1 means generating a pronoun from 0 to 1, and it's the only option. And we would draw it here. Right, so please ignore this stuff doesn't exist yet. It will exist soon enough, but not yet. I want to do this as you would implement recursively. So now our leftmost symbol is this one, non-terminal symbol, and well, we generate an I here, and now we're actually done with non-terminals down this branch. And the next non-terminal symbol is this VP here. This one that was here. So now we entertain the possible ways to expand it, and there is one way or the other. So now there's two options here, expanded, and then we have one option or the other. And then you see that we have two competing trees, this one and this one. And of course, in the spirit of a recursive implementation, this is the one we found first, so let's continue with this. This is the current leftmost non-terminal, so we are going to look for ways to rewrite VP13. VP13 can be rewritten only in one way. So that's a 1VP2 and a 2NP3. So we do that. 1VP2, 2NP3. And now this is the leftmost non-terminal, so we're looking to expanding it. 1VP2, 1VP2 is a 1V2. And now this is the current leftmost non-terminal, and there's only a way to expand it. 1V2 becomes eat. So my tree is much too large, so let me resize it. Advantage of not writing on an actual whiteboard. Eat. Now we are done expanding this branch. This is the next leftmost non-terminal. I also need to make space here. So now we have a 2NP3, and the 2NP3 becomes a 2N3. And the 2N3 becomes pizza. Now this is our leftmost non-terminal, so we have a 3PP5. 3PP5 is a 3P4 followed by a 4NP5. So a 3P4 followed by a NP45. A 3P4, the next leftmost non-terminal becomes a width. And a 4NP5, which is the next leftmost non-terminal, becomes a 4N5. And finally, a 4N5 becomes anchovies. Right? And we're done there. That tree is complete. We can now get to the next tree that was waiting because it still has no terminals in it. So let's expand the VP12. Well, VP12 is a V12, so VP12 is a 1V2, and 1V2 is an eat. Great. Our leftmost non-terminal is 2NP5. 2NP5, well, 2NP5 is a 2NP3 followed by a 3PP5, so 2NP3 and 3PP5. And 2NP3 is a 2N3 and a 2N3 is pizza. And the 2N3 is a 2N3 and a 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 Now I have the 3p5, our current leftmost non-terminal, which is a 3p4 followed by a 4np5. 3p4, 4np5. So 3p4, 4np5. And now our next non-terminal is 3p4. 3p4 is width. Now our next non-terminal is 4np5, and 4np5 is a 4n5. And our next non-terminal is 4n5. 4n5 is anchovies. See that I was writing the rules here, but it wasn't really strictly necessary. I mean, we can just build the trees. And I'm done because there are no non-terminals left to be expanded, and there were no trees waiting to be constructed. So this parse forest contains 2 complete parse trees inside. It's generally not always possible to enumerate all trees in a reasonable amount of time. It would depend on how many parse trees are inside. Maybe this forest has a ridiculous number of valid parse trees, and then it would take a long time to enumerate them all. But in this case, we managed to enumerate the 2 trees that are there. With these 2 trees, what we can do a few things. We can assess their joint probabilities, and because these trees both generate the same string, if we sum their joint probabilities, we get a marginal probability. So let's call this tree number 1, let's call this tree number 2. Now the probability of tree number 1 is what? Well, it's the product of the probability of S becomes NPVP times the probability that NP becomes pronoun, and the probability that a pronoun is rewritten as an I. So I took this product of probabilities of this rule, by this rule, by this rule, and I go on, right? So this rule, and so on and so forth. So times VP becomes VP PP times, now I'm here, right? This branch, VP becomes NP followed by NP. No, sorry, I can barely read my handwriting. It's a VP followed by an NP. Here. And then we go down here. So the VP becomes a verb times the verb is to eat. I'm down here, and now I'm here. So the NP is an N, and the N is pizza. And I hope you see that all I'm doing is gathering the probabilities of the corresponding rules and multiplying them together. Right, so now I have, I'm up here, I believe, and then PP is a P followed by an NP, and then the P is with, the NP is an N, and the N is anchovies. Alright, so each one of these edges has a theta associated with it, and I'm just taking their products. Right, all of them will have thetas that I know if I've already trained this grammar, and I would just take their products, and that would give me probability of tree number 1. Probability of tree number 2 would be, well, the products of all these probabilities here. And what's the marginal then? The marginal probability of I eat pizza with anchovies is the probability you get if you sum all possible, the probabilities for all possible trees. There are 2 trees, so the probability of my sentence, regardless of trees, is the probability of tree number 1 plus probability of tree number 2. this would give you the marginal probability for the sentence. Now, to do it the way I just did, it's necessary to enumerate the complete trees that parse this sentence. Like I was saying, for certain sentences in certain grammars, the number of such trees may be much too large. So you would not want to do this exhaustive enumeration. It's in fact not needed. The PCFG assumptions are such that the quantity, marginal probability, can be computed with a dynamic program that traverses the chart, the forest, solving the problem in a polynomial time. But conceptually, this is how you would obtain the marginal probability. Now that we have enumerated the trees and assigned their joint probabilities, we could also find out the best tree, so the Viterbi tree. Right? The most probable parse is the one of these two whose joint probability is highest. So you would check, is P3 bigger than P3 Yes, so then this is the most probable parse under this model. If not, then this will be the most probable parse under this model. So conceptually, this is how you would solve the most probable parse problem. Finding the most probable parse tree can also be done through a dynamic program. That's the Viterbi algorithm. So the inside algorithm will allow you to get marginal probabilities without this explicit enumeration step. It looks like the forward for HMMs. It's the generalization of forward for HMMs for the case of PCFGs. And the Viterbi algorithm will allow you to do argmax over joint probabilities and figure out what's the best tree without having to enumerate them all. Okay, so in a moment I'll show you the two algorithms. All right, let's talk about dynamic programming for computing marginal probabilities and also mode probabilities. First, I start with some terminology. I'll be calling these things, often I'll be calling these things items, okay? So these are items in our forest or in our chart. And an item, for me, is basically this non-terminal symbol that is annotated with span information, okay? And I know they are unique because remember, anytime we derived the same item, rather than duplicating it in the chart, we have just one instance of it in the chart and we created multiple back pointers. Okay, now any one item, I'm gonna use a function, I will call it BS. It stands for backward star. You don't need to know that too much, but why it's called like that. But the backward star, or the back pointers to an item, the set of back pointers to an item, is basically the set of things that I drew here as incoming edges. Okay, and see that these are fancy edges because they have, they have two children, but think of this as an edge, and the collection, basically this is the set of back pointers or edges incoming to an item. Okay, and an edge, a back pointer or edge, is a rule, a CFG rule annotated with span information. Okay, so you will see here what I mean by this. For example, let's get this edge, the edge 0S5, rewrites into NP0 NP1 followed by 1 VP5. Okay, so that's an edge. What is an edge? How could you represent it? Well, this edge is is the rule SNPVP that starts at 0, splits at 1, and ends at 5. Okay, so it's the rule followed by the span information of how you generate the span and whether or not there is a split point. See that not every edge has a split point. Let's see one that doesn't. This is one. So the edge 0 NP1 is a 0 pronoun 1, and it corresponds to the rule NP pronoun, and the span information 0, 1, so it doesn't have a split point. And another edge that doesn't have a split point is this one here, 0 pronoun 1. It generates an I, and this corresponds to the rule pronouns generate I with span information 0, 1. And see that this also doesn't have a split point. Now, I'm going to give a bit more terminology. This is a terminal edge because its right-hand side, it's unary, and its right-hand side contains a terminal. So the rule's right-hand side is a terminal. This is a unary non-terminal edge, right? Because it's based on a unary rule whose right-hand side is a non-terminal, and this is a binary edge. So that's the terminology we need for me to state the result that I will state next. Now let's think about, maybe now that I have this thing, I can also give you an example of the set of back pointers. So let's make an example of this. So the set of back pointers for 1VP5 is what? Well, it's a set of edges. So we have 1VP5 splits into 1VP3 and 3PP5. Right? So that's this edge, and 1VP5 splits into, what is it that it splits into? 1VP2 and 2NP5. 1VP2, 2NP5. Okay, and from here I can recognize a rule, VP, 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 NP, and I can recognize the span information. 1 splits at 3, ends at 5, starts at 1, splits at 2, ends at 5. Okay, so that would be the set of edges that are back pointing, that are incoming to this item. Okay, let's talk about the value of an edge. Okay, I'm gonna use the letter V for this. So the value of 0SF5, 0NP1, 1VP5 is the probability that S generates NPVP, so it's the probability of the rule times the value of the item 0NP1 times the value or you need a bit more space. Of the item 1VP5. Because the item is binary, I'm gonna get the probability of the item and multiply, and just use multiplication here for now, by the value of this item times the value of this item. And the value of a unary edge unary non-terminal is the probability of the rule NP pronoun times the value well, of the pronoun that we generate on the right hand side. And the value of the terminal edge, 0, 1 pronoun I, is the probability of the rule, so you see that part is always there, times 1. So basically just the probability of the rule. So this value function for an edge will capture the probability of picking that rule and the value of the children of the rule, the right hand side. For the unary case, this means there is only one children, and for the terminal case, we only take the probability of the terminal rule. Okay, with this, I'll be able to state the main result. The main result we're looking for is the value with capital V, is the value of items. Small v is the value of edges. So the value of an item, so a span, right? A non-terminal span. So the value of an item is the sum for every edge that is incoming to that item of the value of that edge. And that's the main result. So we'll be using the forest to compute values of interest, such as marginal probabilities and maximum probabilities. And because of the specific factorization assumptions we make, this will boil down to, for each item, so for any one item we choose, summing the edge values of all the back pointers that can generate that value, that can derive that item, for example here. And the edge value depends on the nature of the edge. For the binary edge, we get the probability of the rule and multiply by the value of the children, of each child. For the unary non-terminal, the probability of the rule and the value of the non-terminal on the right-hand side, the non-terminal span on the right-hand side. And for the unary terminal rule, we have just the probability of the underlying terminal rule. Now let's see the value of an item, specifically where what we mean by value is the marginal probability. So in that case, we call the algorithm the inside algorithm. It's when by value we mean marginal probability. So in that case, what we perform. So let's see. Okay, so we're going to go bottom up, computing all the values of all the items. See that this is a dead end, so we don't really need to compute it. It doesn't continue. This one continues, so we're going to compute this one. It happens to be the same, the same symbol, so 0, pro, and 1. So the value of this thing is basically what? Well, it's a terminal 1, so it's theta pronoun generates I. It's the probability of generating an I from a pronoun. The value of 0 and P1 is what? Is the sum of the values of all edges in the back pointer set. We only have one, so that's going to be what? The probability of generating a pronoun from a noun, from an NP, times the value of 0, pronoun 1, which I already know. Alright, so I could even already substitute here if I wanted. I already computed in the previous step of the algorithm. Now I'm going to compute. See, 1v2 doesn't really continue, so I'm actually not going to bother. I could put it here in the table, but it's never going to be used, so I'm not going to bother. It's actually used in a different item. Just noticed 1v2. Okay, so 1v2. Well, it's a terminal 1, so it's the probability of v generates eat. And then we have 1vp2. 1vp2 is the probability of a vp would be the verb under times the value of 1 v2, and we already know this, it's theta v8, right? It's this quantity here. And you go on. So you will compute the value here. Well, this doesn't continue, though it's used here. So you will compute the value here, which is the probability of n generates pizza. You will compute the value here, which is the probability of this rule times the value of this item. So something similar to this. And you go on and go on and go on. I want to show you what happens as you go on. There will be a point. You will have already computed the values of the inside values of every item, every yellow item here. And then you will need to compute the value, say, let me do one more, of this node, 1VP5. I want to show you what happens at that point. So 1VP5, its value is the sum of the edge values that are incoming, for the edges that are incoming to the node, to the item. So you get the edge value of 1VP5, 1VP3, 3PP5, plus the edge value of 1VP5, 1VP2, and 2NP5. So there is a plus here. Because this is an inside probability, you will compute the probability of going down one way or the other way. Right? And at this point in the algorithm, we would already know the necessary quantity. So this would be the probability of using this rule, VP, times the inside of 1VP5, which we would know at this, 1VP3, which we would know at this point, and times the inside probability of 3VP5 plus the probability of taking the other rule, VP, and P, times the inside of the 1VP2 and the inside probability of 2NP5. Okay, and that's how the inside algorithm accumulates probabilities for alternative derivations. Now I'm going to make a very, very sneaky transformation here and turn the inside into the Viterbi. So the Viterbi algorithm is the value of the maximum probability, or the mode probability, the probability of the mode of the distribution. And surprise, surprise, we are going to simply be changing pluses for maxes. So anytime we're confronted with alternative ways to derive the same item, we pick the one that is highest, that has highest probability. And everything else stays the same. So the edge values are still defined in the exact same way. Only the node value, the value of an item, that will change from the sum of edge values to the max of edge values. Okay, so you would see that for VP5, 1VP5, you would get the, its value in the Viterbi algorithm is the max of this edge, right? So it's the probability of picking that edge choice. So VP, a specific rule, times the value of the children, max the rule probability associated with the other edge, so that's VP and P, and the value associated with the children, so 1VP2 and 2NP5. So that's the only subtle difference. Instead of pluses, instead of aggregating via summation when you have alternatives, you aggregate via maximization. Okay, when you solve the Viterbi algorithm, if you also store the argmax, so for example, when you're here, if the max value happens by following this edge. You store the argmax, right? So the edge, and by making that decision each time, these ones, there's no ambiguity, right? So these ones are the only choices you can make. So I'm just painting them for you to see. Oops. You would be able to, from the very top, say, well, the best tree is this tree. Right, because those are the edges of each one of the items that maximize the probability of the item. Okay, I hope that helps you. This is how you would, this is basically how you think of the inside algorithm and the Viterbi for CFG. PCFGs, they are generalizations of the forward and Viterbi that you learned for HMMs.